say 27, then we have time for questions.
Yeah, of course.
Thanks.
All right, so thanks for inviting me to give a talk here. So today I'm going to talk about neural fields in 3D vision. And the angle that I'm going to take is giving it a maximum posterior perspective to what we've been doing in this area. So I've been actually moved fairly recently to CVPR. My first CVPR paper was in 2020. I used to be a graphics, CGraph, graphics, SGP kind of person. And over the last years, we have been moving toolboxes from the geometric optimization side of things to.
You should be that far.
That far, okay. Okay, maybe I'll bring the ice cream over here. And we've been bringing over tools from the geometric optimization toolbox into computer vision. And a lot of what we've been doing recently has been targeting neural fields. In particular, if you see what is happening this year from my group and my collaborators is basically almost exclusively neural fields, right? This doesn't mean just NeRF, by the way. So the top row is NeRF-based systems, but at the bottom is actually ways of optimizing either side information that you need to train these models, but also things like doing mapping using neural fields or even continuous super resolution using these techniques. So not just doing NeRF, it's just a bit broader than that. But today, I want to talk a little bit about what is the optimization structure of a NeRF model. Not really that much, okay. That's good, yep. All right, so we can start from a collection of images like you see right here. And if the images are calibrated, we can run an optimization problem to obtain these fantastic looking scenes that we've been looking at for a few years, okay? And if you look at the optimization process, is nothing else than optimizing for photometric consistency, right? So you select a random image, select a random pixels, put them in a batch, and then make sure that the color that you predict by doing volume rendering along one of these rays matches the one contained in the ground truth image. And if you actually now interpret NeRF as a map problem, then it should be pretty clear that there is actually the composition of your optimization in several terms, right? So you have certain parts of the optimizations that are taking care of reproducing the data that you have within a training model. And that's actually the job of the photometric loss, right? So this one says given array and given the color of a particular array, whether the model is actually learned properly. And the second one is puts a prior on what a model should be, right? And if you consider the first instantiation of NeRF, perhaps in the prior, you can insert the inductive bias of volumetric rendering, as well as perhaps the spectral bias of MLPs in representing smooth functions. But that's it, right? There's nothing else within a NeRF model to really give you a hand. And so the question the way in which I'm going to present this today is giving a little bit of an historical perspective on how you treat 3D computer vision problems and reinterpret them as a map problem, right? Where you have these likelihood term that tries to find a model that explains the data, and then this prior term that says what are the feasible configuration of your data set to do it. And I'm going to take three different stabs at it according to how I work through these through time. We're going to start from an encoder-decoder architecture. This is a convex net from 2020. We're going to look at auto-decoders with the LOL-NeRF at the previous CVPR. And then I'm going to go a little bit on the diffusion side of things with 3D that we just presented a month or two ago at iClear. So let's start from the first one with ConvexNet. And this is really an historical perspective, right? So the idea back then, and there were many papers that did this, was that to build a generative model, you will have an encoder-decoder architecture. And it looks something like this, right? So if you start from an image and you want to do single image inference, then you will have some CNN of your design, like a ResNet or one of the many others. You will have a decoder, and a lot of the people actually focused on what to put as a decoder in the following years, and then perhaps a VAE-like regularizer on the structure of the latent code, okay? And in this paper that we had back in 2020, the idea was to design a better decoder to then give you a latent space and an output space that would be amenable to downstream application without requiring any conversion. So this is one of the first papers that connected neural implicits to more discrete meshes, right? And these particular case right here, to build a space that is nice and regular, you have to construct a decoder that preserves the structure of this output space right here. So back then what we did is that we said, well, objects can be represented by parts. So we're going to break it into a collection of elements right here and then reassemble them, right? And to build this generative model, then what we're doing is that we are actually breaking down reality into a collection of parts, and each of these parts as a location, as well as a shape that it generates, right? So this is basically the structure of the decoder, and this max operation creates the union from the collection of parts. The differentiable decoder connects like explicit models like polygonal meshes, like here on the left, collection of hash spaces characterized by a normal and an offset with respect to the origin, to a function in space. And this function is smooth and fully differentiable, so we can actually build a training pipeline for polygonal meshes. And if you now look at the latent space, this is what it looks like, right? So you get this really nice, this is actually a navigation of the TZ embedding, and then we interpolate the latent codes in between these data points, feed them to the same frozen decoder, and then see what comes out. And the structure of these latent spaces from the point of view of 3D generative modeling look really nice, right? They really give you a space over which you can do optimization. So if you freeze the decoder and constrain your latent codes to live within the same distribution, they're essentially imposing a prior P of M over data. And back then, these resulted in the state of the art in terms of 3D reconstruction results by adopting such a part-based approach. Okay, but why this path dried up, right? So first of all, these kind of pipelines build a mapping in between images on the left and a 3D representation on the right. And so for you to be able to send gradients through D and to the encoder E, that is the part that is being trained, what you have to do is that you have to have 3D supervision, right? So, and 3D data sets have not proliferated as much as we would have hoped over the last 10 years or so. There is some attempt, but they're not nearly as close in cardinality as 2D data sets for self-supervised learning. And so the question is like, okay, maybe that was the first reason, and this is actually where NERF came in, right? So NERF allows us to move from 3D supervision to projective supervision through images, okay? That's perhaps one problem, but there is a different problem in these kind of architectures, okay? Especially considering this discovery of employing positional encoding to represent the high frequency functions. If you look at the output of what we had over here on the right-hand side, these output look relatively smooth, okay? And that's what most of the results in this topic look like, circa like 2 years ago, roughly. Okay, and when NERF came out, the first thing that I did was I went to Boyang, the first author of this paper, and I said, okay, great. We're just going to go in our architecture. We're going to open up our decoder, and in our neural field, we're going to add positional encoding to the query position we're building, and the results are going to go up immediately in terms of quality. And it turns out that no, like you still get these very smooth functions, and you learn absolutely nothing. So there was something wrong inherently with this encoder-decoder architecture. And this lies in the fact that you have a bottleneck right here, and these latent codes right here are not expressive enough to represent the details on the geometry that you have. So this is where we move to auto-decoders. You know, in the pool of papers working on neural fields, there was also this gorgeous deep STF paper from JJ Park. And in this contribution that we had at CVPR last year, we adopted that way of optimizing within neural fields, within NERF in particular. And again, it's a different way of tackling this problem, right? So rather than building an encoder-decoder architecture, in auto-decoder architecture, you really have a map, right? So you have a term that basically says you want to reconstruct your data, and a term that says that I want to regularize my latent space. So let's see what it looks like. So how do we train? Or the problem statement is that, you know, in the classical NERF model, we have collections of potentially hundreds of images and of a single scene, okay? And so we're going to flip, we're going to transpose the entire problem, and we go from many images to a single image for a scene. And then rather than having one scene, we're going to have many images, many scenes, okay? So it's completely the opposite training dynamics that NERF would have, okay? So how do we do this? Well, we say each scene is represented by a latent code Z, okay? And then we're going to train by auto-decoding. We do not only optimize the weights of the neural network that constructs a scene, but each scene has its own identity, so has its own latent code ZI, and we're going to share the parameters of the decoder across the entire data set, okay? So these can actually overfit on the training data, right? Because these reconstruction loss right here can be made to go to exactly 0, okay? And then it's mostly in the generalization setting that you don't get a perfect reconstruction. But this gives you a way of obtaining a conditional field that represents a generative model of that you need. And then there were a few tricks that we had to do, like injecting some sense of 3D structure within the scene by just using some key point based rough camera estimation. That was worked better than expected. You don't need a lot of precision to do that. And then we had a prior, actually. So if you think about it from the point of view of a map problem, it was not enough to have a reconstruction loss like you can see right here, but we also needed to add a prior, right, that describe what feasible solutions of our model actually were. And for this particular problem, such a prior was very simple, right? It was hand constructed, right, hand built, and it basically took the volumetric integral of NERF And he said that this function W is the weight function for integration, and we can actually put priors on this function W. This function W is the one that contains the geometry of the scene. And you can say, well, but if what we're doing is representing collections of humans, then this function W really only has two solutions in space, right? It can either be a solid surface, so the function should be 1, or it should be representing empty space, so the function should be 0. And so you can design, back then it was one of the first designs of a hand-tuned loss for controlling a map-like problem within under constraints and within under constraint problem. And what you get from this is you get extremely crisp surfaces when you train on a large data set. Okay, so this is first injection of like map-like reasoning within neural fields. And the result that you get, you can see right here. So if you compare it to like GAN systems, you tend to have a better optimization space within which to work. But of course, there's been many works that came out since then. And soon after we had this piece of work, we also had the work from NVIDIA and Stanford, from Gordon's lab, actually, that is going to present next. And what he did then was essentially combine a nerve-like model here on the left with actually an image-based model on the right. And so the difference in between these two works, the one that I just presented and the one that is on screen right now, is really this 2D reasoning model that allows you to go from these smooth signals on the right to these very sharp signals on the left. But I really think that there is hope, right? I don't think we should lose hope and just give up to the diffusion models or GAN models to perform this task. I think there is still hope in whatever is happening right here to get an extremely good results. So it's not a lost battle yet. I'm going a lot faster than I should. All right. So now the question becomes, if I still want to use nerve-like systems, right? Even this paper still uses a nerve-like decoder at this point. Now the question becomes, okay, if I now want to take my data set and I want it to make 100 times larger, then your conditional neural network can be made, perhaps you can take the code and make it larger and call it a day, right? And later on with Daniel, we continue this thread of work, and we actually did an investigation on what is the most powerful conditioning systems for generative models within neural fields. And you might be interested in reading this paper, ABC. The first 3 words tell you basically the outcome of the story: attention beats concatenation all the time, okay? And sadly, I would say, maybe not, but transformers win again. And so basically, if you build the neural fields that use transformers at the decoder layer, you can actually get architectures that have a jump of 4 dB, for example, compared to concatenation-based systems. And you can couple these with like these grids and hyperplanes, like the one you see right here, to get more and more powerful models. So if you want to scale up neural fields, I would suggest you to look at some of this work as well. And we also did a secondary extension to this line of work, which was, well, can we scale even more? Okay, so in these settings, as you can see right here, you have in input the query of the neural field, and then you have your collection of latent codes right here, right? We got a transformer, so the latent code is now a set. But now the question becomes that if I want to go even larger, is perhaps making the set Z either larger in cardinality or larger in dimension the only thing that I can do. And recently, we actually had a paper, a great collaboration with Yasu Furukawa's group at SFU. And Shitao actually found out that having a collection of latent codes at different depths within a transformer can actually be a pretty powerful representation. I haven't had the time to test these ideas in other parts of neural fields, more connected to nerve, but from the point of view of like large-scale localization, it worked out particularly well. Okay, there's even like these are different architectures basically on how to get conditional attention for neural field architectures. All right. So this covers the first 2, right? So let's do a recap again. So we like map. So we know that from a Bayesian point of view, this holds, right? We had a way of doing it with encoder-decoder and, VAE-like losses, and you get these loss of detail in the representation. We can do it with an autodecoder where we can represent functions, but somewhat purely neural field-based systems still struggle a little in terms of high-frequency details, and perhaps is the lack of fine-grained generative modeling that is hurting them there. And there is a bit more to be done there without really just jumping off to GANs and calling it in a day. And then the third kind of like approach that I want to show you on the other hand is when you treat this optimization problem and you basically collapse these 2 elements together. Okay, you have architectures that compound your maximum likelihood optimization together with a prior based optimization that is learned from data. And so these was 3D diffusion models, which as far as I know was the first 3D diffusion paper in the literature. And the results are insane, I think, right? So this is actually trained, is a mapping in between a single image and what the scene will look from different views, okay? This is trained on synthetic data. So this is trained on like ShapeNet augmentation, okay? But then it still works when you throw things that are not part of ShapeNet, okay? And the internals of the structures are very simple, okay? So, and this is done without NERF, by the way. So there is, like, from a point of view of modeling, like the architecture that you need to actually realize these results is much simpler than NERF, okay? So the way in which it works as follows, like you basically say you have a conditional denoising problem, right? Most of you will be familiar with diffusion by now, I hope. And you basically are trying to represent this map problem, and this entire map is actually encoded within this UNet right here. We modified the architecture a little bit, but consider it a UNet for all practical purposes. And basically, for you to be able to generate what will be a scene, like the appearance of a scene from a different point of view, the only thing that you need is you need a reference view, right? So for example, consider this your single shot image representing the scene. Then you need the image that you would like to denoise, right? So this is the denoising path right here. And then the only thing that you need to do then is say, well, given this noisy image and the relative camera coordinates in between this image and this noisy image, please figure out what the noise version of the image is. So the only thing that has 3D knowledge in this architecture is the camera position right here and the conditioning that enters the networks in that form. There's no neural rendering, there's no nothing. And so everything that this model has done has basically been distilled within a 3D UNet. This is a slight departure from, let's say, 3D, purely 3D diffusion model when they have like an underlying NERF, for example, that you're optimizing for. But I think it's still fascinating that you get results that look of this quality. These are actually images scraped from the internet, and the network can actually imagine what that object out of distribution look like from different viewpoints. Make sense? And the underlying architecture to obtain these results is pretty simple as well. So remember, like your model M, so when you're optimizing this guy right here, from a point of view of neural fields, M will be the weights and the latent codes within a neural network to represent the scene, right? That will be the representation. In our case, in this paper, M is a collection of images, right? And each of these images will be attached to a camera position. So what you do is that every new step of this generation process generates the view of a particular object from a never seen before viewpoint, right? And the way in which it works is as follows. In the first step, you take your only, so it's a single shot kind of like workload. So you take your single image, you're denoising iteratively. And of course, because you only have a single image, your denoising element right here depends on a single conditional element, right? There's nothing else but this image to be 3D consistent with. And then you denoise, of course, for a few steps until you obtain the denoise image. And then in step 2, you take the image that you have generated at the previous time step and you add it to the set. And while you're doing this iterative denoising, you make sure that the denoise result is consistent with everything that you have generated earlier by taking a random draw of your conditioning signal. And you do this because having a network right here that is much larger than something that just takes 2 images input can be computationally just too heavy. And so this is a way of amortizing essentially conditioning over multiple images across the diffusion iterations, and they work particularly well. So there's been a number of extensions to this paper right now, even in the NERF domain, but this idea of doing it autoregressively by adding views, for example, still remains. So it's quite powerful. But yeah, like the result that you get are just I would say incredible, right? Like there's no NERF, the results look extremely crisp. And now the question becomes, to me, is how do you integrate this, or should we integrate this with a more classical system, or should we just give up and just pretend that these like green boxes have a full understanding of the universe if fed with enough data? So here are some results of 3D generation driven by images. So we took a prompt, generated an image with some characteristics that match the training distribution, and then he actually can generate novel views from that as well. There is a bit of lack of 3D consistency, so that's where the jitter comes in, right? So it's only stochastically consistent, but not by construction like a NERF model, for example. So just giving zooming out back again, like we had this like history, right? So we started from encoder-decoder architectures. We end up in auto-decoder for a while. And now it seems that I would call them meta-learning, because to me, diffusion models are nothing else than unrolled optimization. But we have this meta-learning way of capturing both the likelihood and the prior within the system. So the question is like, what is going to happen next? And to me, like being able to represent either them combined or perhaps only the prior model effectively is what a 3D foundation model will look like. And there's a few interesting trajectories that I don't know which one I would pick. But one that is particularly interesting is the one established by Dictionary Field. So this is a paper that was not published at CVPR. It's a SIGGRAPH paper, so I would suggest that you just look it up and search it. And I find it like beautiful because it takes ideas from pre-deep learning computer vision, where you were learning like compressive sensing and sparse encoding, and you're learning essentially what a signal will look like as a composition of basis functions. This is a beautiful piece of work from AMPE. And what you can see is that here on the right, if you consider what other NeRF-like pipelines were doing in the few shot settings, where only a few training images are provided, by encoding your signals within this collection of basis functions that are spatially blended, you get extremely good results. So this is what I believe will be one of the main potential trajectories for building a 3D foundation models, right? Scaling these kind of problems with a lot of data and then scaling them in space as well. So another trajectory could be, for example, continuing to pretend the entirety of 3D reality could just be learned by a giant black box. This would be the 3D in continuation. Perhaps that would happen. That will make my job very boring if this just becomes a powerful UNet model with some bit and maybe attention models within. Hopefully that will not be the case. So I hope that the Dictionary Field trajectory will be the one that will survive the test of time. And with that, I'm actually gonna close and take questions. But before I do that, I'm gonna do some blatant advertisement. So we just crystallized the dates for 3DV. So if you're working in computer vision, and in particular in 3D computer vision, notice we put the deadlines for submissions and acceptance, so that it's perfectly sandwiched in between ICCV and CVPR. So you get an extra random shot at submitting a paper before somebody scoops you for CVPR. So we hope to receive many of your submissions, and we're excited to see you in Davos, which is amazing. This is probably the conference I'm looking forward the most next year, just in terms of location. This is where the World Economic Forum is held, by the way, with the hundreds of private jets that land nearby. And that's it. I'm gonna take questions now.
Thanks a lot, Andrea. Let's see if we can also like.
Hello, Prof. Thanks for the talk. And I have a questions regarding recent interest apply the diffusion model as a prior for the 3D reconstruction, like the score distillation kind of stuff. But in my own experience, I find it's very difficult to inject some 3D approach and view consistency when applying the diffusion models to generate some view consistent images. One particular way is like what you do, like you collect the 3D data set, like I train view consistency by applying the diffusion model, but I still think that's way constrained when you apply it in the wild 3D reconstruction or something similar. Do you have any potential solutions on that problem?
So the only reason for which we trained it on that data set was because there were no large data sets of relative camera pose and perso frames, right?
Right. I know there's no that big, like ImageNet level big data sets for 3D multi-view and with post camera. So that's the difficulty now to put this pipeline to real world. So that's right. I'm just seeking another alternative way to do similar things.
But I completely agree with the fact that you shouldn't be doing this thing in 2D, right? Like I would be very sad if we get the job done with just a 2D network. It's like I would be heartbroken. But and so the question becomes like, to me, a foundation model needs to live in 3D, right? So you should be able to just say, okay, this is a chunk of space, generate something, right? There's no image based, like you can train it with images. You should be training with images, by the way, right? But it needs to be an operator that acts on functions in 3D, okay? And this paper that I mentioned from Andreas, I think is one of the first that does that. A lot of the other like generalizable NeRF models were actually not 3D models. They were like image-based models, right? They will learn features in image space, project them back to 3D, aggregate them, and then spit out a function. That's not generalization. You're making, the work is happening in 2D space, not in 3D. some of the works not on the nerve side, but convolutional occupancy networks actually, I think are actually one of the strategies to attach this problem. But I mean, like this dictionary field paper that I mentioned came from the same group, right? So it's no surprise. And so yeah, it's going to be fun to determine how to make this scale and get something powerful out.
Okay. Thanks, Prof. Thanks.
More questions? What about real image? I mean, how do we get away from synthetic data towards real data, dynamic data?
Autonomous driving footage.
Autonomous driving, yeah.
Yeah, I mean, just the footage from the cameras.
James shot outside, yeah.
Yeah, I mean, you know, with him. Yeah, it's autonomous. Yeah, autonomous driving data. I think that's going to be the richest source because we have it. You have to collect it. You have to process it, and then you can learn from
I
it.
think that's the next drop then.
It has all of the it has all the premises that you need to do something. And maybe in the future robotics, but for now that's the robot that we have, right?
Right.
The only robot at scale that we have is the cameras on autonomous vehicles. So it's
Well, some people have access to it. Yeah.
two robots.
Yeah. No, like to the autonomous driving.
Yeah, some people, but it's not gonna. It's gonna be interesting to who can get access to how much information and how well curated and yeah.
Right. It's not just about the scale; it's also
Yeah.
about the curation.
Right. But Matthias, Matthias Nissen was visiting SFU for a defense on Friday, and he's acquiring a data set for this purpose as well. Not from the autonomous driving, but more from the room
Nice.
capture. Yeah.
Talk
So it's
to Matthias then.
yeah, it's gonna be go public sometime. But so that will be. I'm looking forward to that because a lot of it will make possible a lot of the real generalization in 3D space, right?
Right.
Not the projective space one, which is it feels
Fascinating.
dissatisfying. Yeah.
Yeah, at least for some of us. More questions? Come on, it's your chance to ask challenging questions to one of the top experts. Dynamic scenes, like articulated objects.
I mean, the first paper that did dynamic scenes in a memory-friendly way, again from the same group, Andreas does a lot of cool work, was Nerve Player. There has been a lot of work in trying to improve dynamic scene, but it's like I think that the representation is not quite there yet.
What's your shot on the representation? Is there like
I really like hash tables. I think it was a brilliant paper. When I think I was convinced within the first paragraph, the instant NGP paper is like, oh my god, this is like I didn't even see the rest of the paper. That's it. It's like,
but point clouds? Yeah, you've seen the SIGGRAPH paper?
yeah, I've seen the secret paper. Yeah.
Point clouds, the splatting.
But how do you do generative modeling in that domain, right? Do you then need a point cloud generator?
Diffusion models on point clouds?
Yeah, I don't know.
Not convinced.
Not convinced.
Okay.
It's very good for different things, right? Like for different applications, like it's much more friendly to the graphics hardware because points can get manipulated. You can edit it, you can do other things, but from being able to do video and dynamics, you need things to split and merge, appear and disappear. And so you need something, I don't know, I kind of feel that you need something that has a bit more of a continuous nature, less discrete, as you're learning at least. Maybe
Right.
at test time, no, but
Yeah, I got it.
yeah. So I don't know. I'm not convinced by points.
Not convinced. Yeah.
I have one question.
Right. Okay.
So I'm wondering if all our evidence is images, is there any merit in true 3D generative model, or it is better to be nerve-based generative models? Because
Sorry, I'm not sure I quite understand the question. If you have all images, then why
I
nerve is
always
needed?
kind of debate between nerve-based generative models
Right.
versus 3D generative models where everything is intrinsically decomposed, right?
Right.
So, and if all our evidences are images, is there any merit in 3D generative models, or is it better to stay nerve space?
I think it boils down on whether you need assets. So if you're using your generation model for just generating a video directly, maybe you can just get by with just images or videos, and then you're going to be fine, right? Like some of the works in video generation that both Facebook and Google has been doing. But if you then need a 3D geometric asset that you want to generate and then put somewhere else, like in a movie or in a video game and so on, I think that having a real underlying 3D representation will still be pretty useful for at least a little while. fully like neural-based game engines. Yeah, there is some examples, but not fully fleshed out yet. But it's quite interesting. Yeah.
Okay, thanks.
Okay, thanks. Thanks to Andrea again.